Welcome to SingleCrystal 5. In this tutorial, we'll show how you can display a Brillouin zone and measure critical points, distances, and trajectories. A Brillouin zone is a geometric construction in reciprocal space which serves as a kind of unit cell. It's not quite the same as a crystallographic unit cell, which has lattice points at each corner. Instead, it defines the area of space around each reciprocal lattice point. This is useful when considering wave vectors, which typically lie between reciprocal lattice points. We construct the first Brillouin zone by considering the closest neighbours of a reciprocal lattice point. In this 2D section, the first nearest neighbours are red, and the second nearest neighbours are green. We take the bisectors of each vector and take the minimum area or volume enclosed. For this simple square lattice, our first Brillouin zone is a square centered on the origin. We could go on to define second and third Brillouin zones, but for the purposes of reciprocal space and wave vectors, these aren't really necessary. Now let's extend this to 3 dimensions. We'll start with a simple cubic material with a primitive lattice and load its structure into SingleCrystal. Here we can see its default TEM diffraction pattern. We want to show the Brillouin zone around the centre of our pattern, and we want to show this in 3D. To show the first Brillouin zone, we use the Simulate 3D Brillouin zone command. We can see that this has the shape of a cube and that the surrounding reciprocal lattice points are drawn as tiny spheres, each one being labelled. We can rotate and zoom the display and also set a specific view direction. Here's the square shape section that we defined for our 2D reciprocal lattice. We can measure the shape and important points using the arrow tool from the tool strip. If we hover over a face, its corners, edges and centre are highlighted. Hovering over a point causes an info tip to be shown with the coordinates of that point, and expanding the info tip gives the length of the reciprocal lattice vector from the origin to the highlighted point. We can also select one or more points and define a path between them. We use Shift-click to extend the path. And notice that I also selected the origin. This was a very simple cubic p-lattice. But what about a non-primitive lattice? This is where things start to get complicated. Here we have the Brillouin zone for a face-centered cubic lattice. Why isn't this cube-shaped? Well, let's take a look at the reciprocal lattice points. And this is probably easier if we turn off the lattice mesh. We can do that by going to the inspector and the reciprocal lattice group, and let's turn off the mesh. Notice that the 110 points, such as this one, are marked with crosses. These correspond to systematically absent reflections. They're lattice absences caused by the face-centered cubic lattice. Basically, our cubic F unit cell is 4 times larger than it should be. And when defining the Brillouin zone, we need to exclude these points, resulting in a more complex shape. We can customize the display using the inspector, hiding points, labels, and axes. We can color the faces of the Brillouin zone using the coloring group. Coloring by symmetry, by stereogram pole, by numbers of vertices, or uniquely by individual faces. And there's even a minimal coloring which will apply the smallest number of colors necessary to differentiate faces, and we can change the opacity. Let's color by stereogram pole, and let's go to the extras group, and let's do show in stereogram. Turn on our floating stereogram, and here now are the normals and the traces to the planes in our Brillouin zone. Finally, we can compare multiple Brillouin zones in the same document. Let's compare our primitive cubic one with this face-centered zone. Both structures have the same cell parameters. We'll start by opening our sidebar and choosing the Add command. And let's choose a document on the desktop. Next, I'll set the same orientation for each structure. And let's set the orientation to the Z-axis, or C, and for this one as well. Finally, I'll select both thumbnails to show the displays superimposed, and the way to do this is to hold the Shift key down on your keyboard and then click so that they're both visible. We'll make sure that the opacity of these planes is slightly less so that they're both visible. Notice the difference in volumes of the two Brillouin zones. Why is this? Well, remember that our cubic F structure has the same sized unit cell in real space as the cubic primitive structure, but 4 times the number of lattice points. In other words, its true primitive cell is 1/4 the size in real space, and hence 4 times the volume in reciprocal space. So that's a brief introduction to Brillouin zones in 3D using SingleCrystal 5.